get loaded. And of course, the old-fashioned way in a contiguous memory allocation. So once it gets, if it is uh, installed, if it is loaded in contiguous allocation, then in contiguous spaces on RAM, then of course it's a sequential stream of execution. As I may have pointed out at that stage, that pay attention to this word sequential. Don't confuse this word. Don't confuse this word sequential. Sequential doesn't necessarily mean one after two after one, three after two, and four after three. That's not the way the algorithm works. It depends on the kind of algorithm that you have mentioned, you have written inside, or you have implemented rather, inside your program. So based on that, it could very well be the first line will be executed first, and then the CPU will be pointed to line number 3, to line number maybe 10, and then line number 10 back to line number 4, back to line number 3, line number 3 to line number 2, to back to 10, and then on. So whatever way the flow of logic has been defined, or flow of control inside the program has been defined, that's the way the things will play out. The sequential execution will play out. But CPU, as long as it is executing that particular program, that particular process, must be within that program's own address space, even on RAM. Okay, so that is what it means. Moving on, we try to build a model of the process. When you try to build a model of the process, you need to understand the several factors. The early computers that allowed only one program and execute the time, or the quantum, or the slice of time. The slice of time. In fact, in early computers, we didn't have multi-programming. So since we didn't have multi-programming, the things were kept pretty simple. These were mostly batch processing systems. These are mostly batch processing systems. And in the batch processing systems, it was one program at a time that was getting executed. So one program at a time getting executed on RAM. And as usual, the batch processing, when you start a program, you're not supposed to, you start a process, you're not supposed to interrupt it. In other words, of course, you can't interrupt. The OS will not interrupt. It will take its own sweet time to voluntarily exit or terminate, or just simply block itself, whatever as per the programming codes. And that was exactly how it used to play out. All right. The next thing that we are looking at, as I already mentioned, the program is a static entity, and the codes, when they're loaded as a process in RAM, they become active. And we call them active because they sort of acquire a whole bunch of resources, a whole bunch of things, right? Eventually, we'll get to see what they acquire and how these things are carried out. A process is a program input, output, and a state. The most important thing. A process has a state. Now, what exactly we mean by this word state? By the word state, we exactly mean what we exactly mean is the value of its registers and PCs and all the other things that in between we have. So that is what we call the state of the process that should be saved. So that is exactly what we have. And when it comes to the implementation of the process, we have two parts, and the most important part being the second part that you can see, process state. Everything this process interacts with registers, the memory, the files, and etc. during its runtime. And that is what we call the process state. And this state must be saved. This process state must be must be saved every time a process gets switched. So this some ideas, these basic ideas will help you to build a model of the process that we are working on. If you move on, you can see there in the next slide, they have given two pictures, the first one and then the second one. So basically, we already know the first one and the second one, two of these, are the two ways the instructions are implemented. The instructions are implemented in two different ways. The two different ways the instructions are implemented. The first one, we know, is what we called a pipeline execution. That means one CPU, and that's the most common one, by the way. Fetch, decode, and execute. That is the cycle that keeps going on. So one PC, one program counter, and program counter will fetch the instruction, then it will decode it, and it will hand it over back to the ALU, or the arithmetic logic unit, and each of those that instruction will be executed by ALU, and that PC will be moved to the next instruction. That's the most common way of execution. The second one that we are looking at on the right-hand side of the screen is what we call superscalar CPU. That means where multiple program counters are working together. And these multiple program counters, definitely since there are multiple program counters, they will fetch multiple instructions. And multiple instructions will be decoded at the same time, but will not be executed parallelly. They will be stored. Okay, they will be stored in what we call holding buffer, and then from there, those will be executed. Now, if you move on, in whichever way we choose to implement the execution of instructions, it will always look to us as if this, as you can see in the third picture at the bottom, the ABCD, these four processes, are running parallel to each other. That's our impression. That's what we believe they are doing. So we have this this person, the user, standing outside. Just imagine yourself that you are outside the system, and you're looking at your computer screen, and you start believing that your ABCD, these four processes that you have started, they are running parallel to each other. But they're not. But if you take a system view, then you understand that yes, four of them are all on RAM, but they're not getting executed parallelly, right? They're taking their turns on CPU. As you can see, D was the first one, and then move to A, then A to B, B to C, C to D again. Now, that is the way the things are getting executed. And this is what we refer to as pseudo-parallelism. Right at the beginning, you can see pseudo-parallelism. Okay. In a single processor system, it is a common feature. If it is multiple processor, so that means at least two of these instructions or two of these processes can run parallel to each other, right? But a single processor system, it is and it has to be pseudo parallelism. Multi-programming is all about switching among processes, and the CPU keeps switching them, switching from process to process. And this switching action is what we call, context switching. Context switching. I've tried my best to highlight these words as best as I can, and because this will help you to remember these words. So these words are vital. So later we will be using these words here and there quite often without explaining what these things are. So once you hear these words, it must click in your mind what these words mean, words and expressions mean. Switching the CPU to another process. Now, it is not that simple. Like we may say that it's very simple. It's just block a process and put the CPU to another part of the RAM. But that's not the case. In between, there's a lot of things that OS needs to do. So first of all, the old process that is going to be blocked, or the CPU was previously working on, its data needs to be saved. And all these registers value, because remember, when a process is running, all its register values, okay, that means all its properties and other values must be loaded on the PC register. So you remember inside the PC that we had almost n number of general registers, and these values must be saved. So the both way. The first thing that we do is a process that is getting blocked. Its current register values must be saved somewhere permanently. I mean, not exactly permanently, but temporarily. Must be saved. And we will mention it later, where exactly it is saved. Number two, towards the end of that shifting process or switching process, OS must reload the previously saved values of process 2, that means the current process is going to run on CPU, into the CPU registers, and only after that the CPU can start execution. Now, depending on what kind of underlying hardware you are using, there could be a slight delay. Delay or time lag. That means a process has been blocked, the new process hasn't yet started running or executing on CPU. And this tiny amount of delay, usually it is imperceptible, that we can't really feel it. But if there is a delay because of the hardware, this delay is an absolute wastage of the CPU time, because CPU is idle. But remember, CPU is one of the most expensive and most important resources that we have inside the computer. Right. And like any other important resource, we want to utilize it as best as we can. But now there's no chance, because the CPU is waiting in an idle condition while operating system is getting things ready to switch the CPU from process 1 to process 2. This is what we call an overhead. As you can see, I've highlighted this word, and this is a very common word we use in computer science and information technology. Also, these words we do use in a casual way as well, because we mean overhead. Overhead literally means that you are using a resource, the resource is running, but it is unproductive. It is literally unproductive. It's not doing any fruitful job. Okay. So basically, it's very similar to that I've hired someone with a high salary, but I can't give him any job to do. So basically, he is sitting there doing nothing. So that is what that is what we call a pure computer overhead. And that is what exactly we mention by the word pure overhead, depending on the hardware and the machine. Okay? And that can create a kind of bottleneck for the situation, bottleneck for the computer. When it comes to process hierarchy, I think I mentioned it earlier. Uh, process hierarchy is not supported in the Windows by Windows in Windows environment. It's an old Unix level thing, and that is what we do. So you can see, in fact, in Unix we have a system called mount and unmount that helps the system to implement these hierarchies, right? But if you look at the bottom of the slide, you see we clearly mention that Windows don't support it. Okay. And that's why that mount and unmount system calls, they're missing in the Windows context. Clear? There is an important issue. That is called process termination. How do we terminate a process? Well, when it comes to process creation, of course, we understand who creates the process. Well, sometimes the user, they want to run something, or it can be another process that will decide to run something, so, create a process. So that is process creation. Now, when it comes to termination, however, there are four typical ways that we can terminate a process. The four typical ways. The first of it is, as we can see, the first two, in fact, are voluntary exits. First two are the voluntary exits or voluntary terminations. So what do you mean by voluntary termination? Voluntary terminations literally mean that programmatically we exceed the RAM. Now, the first one you're familiar with, probably some of you already know the second one as well. The second one we can implement. That means we run the program, and when we expect that there could be an error, we catch the error and we kind of stop it from flowing, this error from flowing into the other parts of the program. Now, why we do it? We do it simply because we don't want the rest of the program, the entire program, to get choked with that particular error. So that when it happens, we just give a system call. These things happen with the system call. We also have involuntary exits. And when involuntary exits, the name itself tells you what happens. There must be an error, a fatal error, an error. It could be a programmatic error, it could be a hardware-related error, but that has not yet been captured by anything. So that is what we call the programmatic error. Now, once we have the programmatic errors, then or fatal errors, then definitely it will run into, it will terminate. It will abruptly end. Now, if it terminates, or even worse, that if it somehow has a negative effect on the entire program, the program might crash. So if that happens, it usually happens through interrupts. It usually happens through interrupts. And we know what interrupt is all about because it is a hardware trap, and definitely the machine will have to abruptly kill that particular process. If it doesn't, then the machine itself will go into a hang condition, will become non-responsive, right? So we need to understand these four different ways that it can terminate. Also, a process might like to kill it. So in whichever way it terminates, the first two are the most acceptable way. The last two, when they happen, that the involuntary exit, it may cause some other related problems. Okay, it may have certain other consequences. So we need to be careful about these little things. Remember system call and interruption, receiving and interruption. Let's talk about process states. How many different states we have for a process? How many different states we have for a process? How many different states we have? Well, as we mentioned earlier, there are three initial states, the three major states, or I should say three stable states, and two of them at the bottom, we say optional. Basically, it's a transitional state. These are transitional states because when a process is newly created, it should be put into the new state. Well, that doesn't necessarily mean that the new state will stay for a long time. It won't be staying there. So it will eventually pass on, so move on to one of the stable states. Right. The one thing that is important what happened? So the states that we are looking at is pretty easy to remember. Running, ready, blocked. And now you understand that when previously when I asked you that definition of a process, and you said a process is all about a program in execution, a program running on RAM, and you used the word running. I was not very happy with the word running. I didn't accept it. It's because a process can have different states. It can be running, it can be ready, or it can be blocked. At the same time, two optional states, new and terminated. The most important thing is this one. And do expect at least a question from this part. And I will. You pay attention to this, and later I'm going to ask you a question on that. Transition of states. So one thing we must remember, that transitioning from one state to another state, some of these transitions are permitted, are legal, are allowed, but some of these are not allowed. So the question actually arises that which ones are allowed and which ones are not allowed. For example, the first one, as you can see, if a process been newly created, then it can either, from there, it can either go to the ready state, or it can directly be given the CPU and it directly start running. So naturally, these are the two things that we need to pay attention to. The first one and the second one. Moving on, the next one. If a process is in the ready state, from the ready state, the only thing it can do is to go to the running state, nothing else. From the ready state, if a process is still in the ready state, it can't get blocked. It can't get blocked. Okay? It can't get blocked. So it can only, from the ready state, it can only go to the running state. And then the next one that we have is the running to ready state. Running to ready state. If a process is currently running, it can be put back to the ready state. Then running to block state. If a program is currently running, it can be directly blocked as well. So a program which is currently running, it can either be put into ready state or blocked or even terminated, or blocked to ready state. Okay. And then finally running to terminate. Clear? Take a minute to look at this picture. And then the kind of questions that you will get in the exam, I'm going to ask you one such question. Okay. So my question to you is, and I move back, my question to you is, listen to me carefully. A process is currently blocked. A process is currently blocked. OS, or operating system, wants to kill it or wants to terminate it. Wants to terminate it. So the point is, it is currently blocked and the operating system wants to terminate it. So my question to you, in that scenario, how will this process currently blocked get transitioned to termination? How will this process, which is currently blocked, will get transitioned to get to the termination state, or to get terminated? So how will it happen? Anyone can suggest an answer? The process is currently blocked. In fact, I can give you options. I'm not giving you options. I keep it open for you. It's currently blocked and OS wants to terminate it. So what are the states that it will have to transition through to get to that terminated state, to get to terminated? Will it be option one, blocked to running to terminated? Will it be blocked to terminated? The second option. Third option, will it be blocked to ready to terminate? So three options I'm giving you. One is blocked to terminated. One is blocked to running to terminated. One is blocked to ready to terminated. What do you think? or anything else? Any of you give me a lead on that? You can type your answer if you want. This is the kind of tricky questions that they will ask you. Tricky conceptual questions. Blocked, ready to running to terminated. Excellent. You nailed it. You nailed it. Thank you very much. And probably you are the first one, trust me. I'm not sure if in the last class I talked about it. It was a tricky question. And you are the first person over the last almost 3.5 years that right at the beginning, the first answer you gave is correct. Okay, I tell you, most of the students, they don't give me the correct answer. Great. It must be, thank you, from blocked to ready, ready to running, running to terminated. So the 3 options that I gave you were incorrect. It should be none of the others. Okay, option 4. So now you understand that how important this particular slide is. It's a very tricky, simple concept. But now we are in the context, so you can give the answer. But just out of context, when suddenly someone asks you this question, you need to be careful, right? So we move on and see what else we have about the implementation of a process, how the process is implemented by operating system. Talking about implementation, we already mentioned the word abstraction. Implementation is in fact what we refer to as OS or operating system abstraction. So what do we have to start with? It's all in the hand of the kernel, because that's it. Like it's, as we say, the process management or process implementation is entirely controlled by kernel. So inside the kernel, we have 2 important things. The first one is a register, and the second one is a whole bunch of algorithms. The first one is what we call the process table. It is one of the vital registers that kernel has to keep control on these processes or the various activities of these processes. So it can keep an eye on the process table to know exactly what is going on inside most of these processes, right? And now, as we said, it's a kernel level register, one of the most important registers. But as usual, we the users, we are not supposed to have a look at these registers because these are part of internal matters, internal environment of the computer. So we are not supposed to know exactly what is a register and how it looks like. But it gives you an opportunity to look at this particular process table or kernel level register. Okay. This kernel level register or the process table is what we, the users, from our point of view, we refer to as task manager. That's what we do. That's what we call a task manager. So what is a task manager? Now, task manager is something that is quite familiar to us. Well, in Windows environment, Microsoft on purpose has grabbed that register and pulled it out on demand. Of course, you have to press Control Alt Del to get the task manager, and then put it in a beautiful visual GUI environment, GUI interface, and presented it to you. With, of course, only one action button, and that is the purpose because of which we need to go to that particular interface. And that is kill the task or end task. That's the only button that you have right in there. Right. So if you open Task Manager and you don't have to kill any process, you just keep it open and keep looking at it, and you will see how these values in those cells, various cells, they are rows and columns, and the intersection of row and column is a cell, and there are some values there. And these values are getting randomly changed in real time because these are all registers. And that's how they work. Okay. So what we get is a process table, and inside the process table, we have a process control log, or PCB. Okay. And at this stage, we are not talking about, we are not talking about the scheduler, because that's another component that we talk about later. And that component has a whole bunch of algorithms that will be used for switching, okay, for the switching of operating system, switching of the CPU by operating system. Right. So that is what we do. That is what we do. So we have a PCB, a PCB associated with each process on the process table. So we have a process table, and the process table, each process table of the register is associated with a PCB. So basically, that is what we see inside the task manager. Inside the task manager, these are the things that we'll be looking at. So that is what a PCB block is all about. If you put it in a visual way, so basically what we mean is there we have the task manager. That's the process table. You have rows. Each row is a process. That means it must be loaded on RAM at the moment. And then we have multiple columns. At the intersection of these columns are the cells. And these cells store vital information, key information of all the register values of that process state. That is what we were talking about. Now, as I said a few minutes back, that when it comes to switching, the first thing that operating system will have to do is, after blocking a process in CPU, is to save its current register values somewhere. And this is exactly where these are saved. So this entire block of information is what we call PCB. So this is the PCB for process 1. The next one will be the PCB for process 2. The next one will be PCB for process 3, and so on. So that is The things that we are looking at right here is multiple PCBs for multiple processes. So any process, whether it is currently executing or it is blocked or it is standing in the ready state, it must be associated with a bunch of register values. And these register values are the ones that will be stored inside the PCB. So it must have PCB. So that is what these things are all about. So the PCB that we are looking at is associated with any process that is currently running. Clear? So when we get to know about that, the PCB, then the next part that remains is scheduler. But we're not going to study scheduler right here. That's another module. And that is where all the algorithms have been defined, as I say. And we will study it in the later part of this chapter. So broadly speaking, the entire implementation takes place in this way. And as you can see, the most important concept in this particular picture the ones that we are looking at the moment is how the context switch actually takes place. And as you said, there is a whole number of steps, a bunch of steps that the OS will have to do, OS will have to go through to implement this switching. But at the very onset, at the beginning, the first thing it will do is to save its registers values in the PCB. Okay? From the registers of the CPU, those values will be transferred immediately into PCB, which is another register, from one register to another register. And then it will do a number of other things. The final thing that needs to be done is to reload the already saved values of the second process, or the current process, or the incumbent process, into the registers, into those n number of registers inside CPU. Only after that, it will let CPU work. Our CPU can actually start executing those instructions. Okay, so that is exactly how these things get carried out. So in between, there's idle time. And that's what we're looking at. So CPU is idle. And if CPU is idle, as I mentioned, then it should be considered as a computer, as computer overhead, because CPU is unproductive while the machine is running. Because neither CPU is working on process 1 nor on process 2. This idle period is also referred to as latency time, as you can see right here. Please take note of this particular word. Latency time. It's also referred to as latency time, and we must try to reduce the latency time as much as possible. Because the latency time, if it is too long, then that means your machine is slowing down. Okay. So we should avoid latency time as best as we can. Clear? The next thing that we are going to talk about is an interesting feature inside process, which we called the degree of multi-programming. Okay, the degree of multi-programming, and is directly related to one of the most important concepts in OS, operating system management. That's called CPU utilization. In fact, CPU utilization is considered one of the most important criteria in evaluating, when it comes to evaluating the performance of a particular type of operating system. That's a batch processing operating system. CPU utilization is also one of the most important criteria based on which some algorithms are implemented. For example, prioritization, priority-based algorithms. That means not all processes have the same priority inside your operating system. Some of them are high priority processes because they need to be kept running. They should be running most of the time. So naturally, they have the higher priority. So as I said, the while kernel dynamically on the run does this kind of calculations to decide which of these processes should be a high priority process. It takes into consideration one of the most important criteria, and that is CPU utilization. That is what it does. CPU utilization. So let's just move in to see what it is. To keep it simple, we must mention it at the beginning. That look at this word, utilization. Utilization and usage. Let me use these two words. And I'm sure that most of you understand the difference between usage and utilization. To understand it in a very simple way, let me give you an analog. You go to the market and you buy an apple, and you pay, for example, $5 for that apple. But the question is, why did you pay $5? You paid $5 because in your estimation, this apple promises a nutritional value worth $5 or more. Well, that's a different story. So when you buy an apple, it has a total nutritional value that is 100%. The apple that you are holding in your hand. Okay? If someone can consume the whole apple, you will get 100% of its nutritional value. Now you bring it back home and you start eating it, and you ate half of it. See? And the other half you couldn't finish, it's too big, and you just threw it out. That half, that part, is wasted. Now, if someone asks you this question, then how much of that particular apple you actually consumed, you actually used, you actually ate? That is the usage. The answer is simple, 50%, because you ate half of the apple. Now, if I switch the question from the apple's point of view, and I rephrase the question in a different way and ask you, can you tell me how much of these apples' total nutritional value was actually utilized? how much of these apples' total nutritional value was actually utilized. So you can see I've just flipped the question, but it means something different. You will say, oh, yes, 50%, because 50%, half of it was eaten and half of it was wasted. Now I changed the scenario for you. Think about it. Now, you bring the apple and you eat half of it, but instead of throwing away the other half, you share it with two of your friends and they finish the other half of the apple. Now I come back to my old questions. How much of this apple you actually consumed? 50%? Because you ate half. Now if I flip the question and I ask you the second one, how much of the apple's total nutritional value in this new context has been utilized? The answer is 100%. So your usage is still 50%, but the utilization of the resource is 100% because you didn't waste the other half. It's a very important concept. Now you'll see why I mentioned this thing. Now you move on to see we have a very simple equation here, and I strongly recommend and advise that you try to remember this kind of simple equations. Okay, just in case you never know, they might ask you to do the calculations. They've given an example, and let's move on to see the example. What do they see? A computer has 512 MB of memory, with OS taking 128 MB, and each user program also taking up 128 MB with an 80% average I/O waiting time. If you put this into that equation, put these values into the equation, so this is what you get. $49. In the current scenario, it is 49%. Okay? So that is what we get at the moment. Now we change the scenario. And what is the new scenario? The new scenario is we add 512 MB of extra RAM. And then we go back to do our calculation and we find a huge jump in CPU utilization. Now remember, our target is to utilize the CPU as best as we can. It must be around 90%, 80% or 90%. That is the best utilization most of the time. We don't want to underutilize it. That is what we do. And so we get CPU utilization. Now that's good, that's fair enough. But how will you put it? So if someone asks you how can we increase the utilization of CPU, the answer is very simple: increase the RAM. Increase the RAM. But that is according to the calculation that we have. That is according to the calculation that we have, according to the equation that we have. But how will you logically put it into the perspective, right? So though we have another 512 MB of RAM that we have. Once we have this extra RAM, and how will you put it into the perspective of exactly what is happening? Logically, well, extra RAM means more space on RAM. And more space on RAM means now you can accommodate more processes on RAM at the same time. More processes on RAM means more mouths to feed. Literally. Think about the Apple analogy. More mouths to feed. That means now you can switch the CPU among more processes. So the more you keep switching the processes among more processes, better it is for increasing the CPU utilization. So essentially, the reason behind it, and that's why we are going to expand the RAMs, because we want more processes among which we can keep switching the CPU. And if we can do that, then we can see that they are getting the utilization, the CPU utilization is going up and up and up. Okay, so that is what we are looking at the moment. Clear? So that is what we have. If you have any question up to this point, feel free to ask me. It's all about processes. And then after this, we will move on to threads. Do you have any question from this part? Any of you? Feel free to write in the message. Apparently you don't have. So you're not asking me any new question. All right. That brings us to the end of this short part called process. So a quick review of what we learned. We learned a few definitions, key definitions. In fact, these three definitions gave us three different perspectives of what process is. We also discussed the process model. We tried to understand the model. That means exactly what process is and exactly how it gets switched. That is what we understood. We understood how it is implemented on a multi-programming computer. So this and a few other things that we talked about was CPU utilization towards the end, the process termination, and process state. So these are some of the key things that we have studied so far. To move on, we will, if you don't have any question, then we will move on to the thread and still we have a little bit time, so might like to get started with threads. Strongly recommend that after attending these lectures, you should go back and study the book in more details. You will get to know a lot of things, and if it's still not clear in your mind, then get back to me and ask me questions. So we're into the new part. That is what we call threads. Okay. So what exactly is happening inside threads? What is a thread? If you don't have any perception at this stage about what a thread is, the way I like to define it is these are multiple channels of sequential execution of codes inside a process. I repeat, multiple separate channels of sequential execution of codes within the process environment or inside of a process. That's how we define it. Channels. So previously, in single-threaded programs, we were running a line of instruction. But now, inside the process, we create multiple channels of the sequential instructions. So at any point of time, during the runtime of that process, only one thread is getting executed. But why threading? Why do we go for threading? What are the key benefits that it brings? The first few slides are all about the reviews of the process that we went through. Now, these are some of the things that we'll be looking at. Models, benefits, and 3 different kinds of implementation, and a little bit of scheduler activation towards the end. So let's move on and see what we have inside the context switching. Now, the issue that we address here, the reason that we had to think about multi-threading. But remember, multi-threading is optional. It's entirely up to the programmer or the developer to decide whether they want to implement multi-programming or not. Okay. They don't necessarily have to implement multi-programming. When you are writing a program, you don't have to necessarily make it a multi-threaded program. It's optional. But there are some key benefits that we get when we make it multi-threaded, right? And what are the key benefits that we have? Some of the key benefits that we are looking at is, think about it, that you are typing an important document, and it used to happen to us in the older versions of Microsoft OS. And then you forget to click the save button to save a copy of your file of the data from the RAM into your hard disk. And then suddenly there was a power failure. And it used to happen quite often in the past. And those computers, those big desktop computers, if they're not connected to a proper UPS, just kind of a power reservoir, but UPS, then it will suddenly crash, black out. All the important things that you had written are gone. But now, if you use multi-threading, you can in fact use a thread. You can write a thread, and that thread at every 5 minutes or every 2 minutes, it will run, it will wake up and run automatically. And its job will be to save a copy from the RAM into that hard disk. So that is exactly what one of the things that one of the benefits, the key benefits that we could think of. It was the same thing with emails. I still remember in the older emails, before Gmail came, we used to use the Yahoo mails, the Rediff mails. We didn't have this multi-thread interface. It was like you were writing an important email, and suddenly someone gives you a call, and you unmindfully, carelessly, just close the browser. You forgot to click on the Save Draft button. There used to be a Save Draft button. If you click on the Save Draft button, a copy of this email will be saved in the server. But if you don't click on that, then all the good things that you had written will be lost. But now, it actually started happening with Gmail. When the Gmail came to the market, right from the beginning, they implemented a multi-threaded operation. And what was that multi-threaded operation? That now you don't have to worry about saving it manually. These are auto-save. As you keep typing an important email, every 1 minute or every 2 minutes, Google is saving it into a draft. So how do they implement it? Threads. Another example of threading, and this is the most common one you see every day. You start Microsoft Word or PowerPoint. Then you want to open a new PowerPoint window. You go to File, click on New. What you are creating is not a process. You're actually creating a thread. And that will actually bring you to the second benefit and the most important benefit of threads, thread implementation, of multi-threading. The speed of thread execution, thread creation, thread termination, and thread execution is much faster, almost 100 times faster than process creation and process termination and process execution. The reason behind it, as we will see as we go deep inside the threads, is that threads are primarily implemented from the user mode. Kernel hardly ever gets involved in thread implementation. And the speed that I'm talking about is obvious to all of us when we try to open this new PowerPoint window. The first time you tried to open it, it was quite slow. You had to wait. But now you go, when it is open and running, you go to the file, click new, you will see in a split second the new windows pop up. These are all new threads that you are creating inside that process. And you understand the difference in speed. It's much faster, much faster. So that was the key benefit. This picture will explain what we mean by threads. This on the left-hand side is process, and how processes are taking turn on CPU. This on the right-hand side is inside those processes, if they're multi-threaded, how the multiple threads are taking their turns to run. Thread A and thread B. So these two are also getting context switch, but there's a little bit of difference. And this little bit of difference is that In case of process switching, everything is controlled by the CPU, by the operating system, by the kernel. In the case of internal thread switching, it's primarily controlled by third-party software that is called the runtime environment, which is in the user mode. And since it is from the user mode, there are possibilities of overlap. It rarely happens in the case of processes because everything is controlled by kernel. As we always say, that if you go to the kernel, your service is guaranteed. You don't have to worry about any service level failure. But if you try to do something from the user mode, you gain on speed, but there are chances of overlaps. And that's the reason we have used right on the top in the definition, you can see the new word quasi-parallel. Remember, in the case of process, we use the word pseudo-parallel, but you are not exactly mentioning the word pseudo-parallel. It's in quasi-parallel because from time to time there are chances of overlap. A little bit of an overlap. Okay, so these things can actually happen. So there can be chances of overlap. They are overlapping each other. And if these overlap happens, then there could be your system could actually run into a potential race condition. I avoid the word deadlock because later we'll explain what is race condition and how your system runs into race condition. And that is exactly what happens when you go there and try to execute it. So we'll stop here because we will come back and get started with the threads once more. And we'll try to move forward from there. We do have enough time, and we will probably be needing this week and another week. We'll move into next week to finish this chapter because towards the end, it will become more and more critical. All right, I'll take your attendance. It's a little bit of noise coming from the kitchen. Lock the door. So anyway. Okay, please respond. Xuan Huang.
Yes.
Chi Kang.
Yes.
Vin Phúc. Vin Phúc. Juk Huang.
Yes, yes, yes. Yeah, me.
Luang Ha.
Yes.
Hu Huang. Hu Huang. Tan Hum. Tan Hum. Nop Phat.
Yes.
Din Min.
Yes.
Quoc Huy. Quoc Huy.
Yes. Yes.
Wai An.
Yes.
Kim Thắc.
Yes.
Nhật Min.
Yes.
Thanh Phúc.
Yes.
Quang Huy.
Yes.
Minh Khôn.
Yes.
Duy Bao.
Yes.
Quay Min. Wait. Liêm Trúc.
Yes.
And Quoc Hum.
Yes.
Tan Hum.
Yes, yeah.
Hu Huang.
Yes.
Luang Ha. Okay, the others are done. Vin Phúc.
Yes.
Vin Phúc.
Yes, teacher.
Okay, it's still there. All right, thank you. So we'll see you on Friday. 15 days more. All right. Have a nice day. Bye.
Goodbye, teacher.
Goodbye.
Goodbye.
Goodbye.